Sorry about the interruption. I'll be starting it once again. Okay, so
Okay, so
we're discussing about the different methods of finding the mean rainfall over a drainage basin. So the first method is the arithmetical mean method. This is one of the simplest method. It is nothing but finding out the average of all the rainfall from that is collected from all the rain gauges that is placed in the drainage basin, and finding the average of all the rainfalls. A simple arithmetical calculation. You add all of it and divide it by the number of rain gauges in that particular station. The second method is a method called the Thiesen's mean method. Now, in this method, uh, we can see here that this is the drainage basin that is under consideration, and these are the rain gauges, the ones numbered 1, 2, 3, 4, 5, and 6 are the rain gauges that are placed in the drainage basin. Now you can see that only the rain gauges numbered 1, 2, and 4 are placed within the drainage basin. So what we do is we consider the nearest rain gauges adjacent to this drainage basins also, and connect these rain gauges in the form of triangles. So you can see this one is connected as a triangle. Then there is 1, 2, and 6 connected as a triangle. There is another 1, 3, 4, 5, and all of these rain gauges are connected with each other to form triangle. That will be the first step. So after that, what is done is, okay, after that, what is done is the perpendicular bisectors of these triangles are found out. So you can see that the perpendicular line from here, from this side of the triangle, from that side of the triangle, and this side of the triangle are going to meet at this point. So that point is marked. Similarly, the perpendicular bisector of this triangle is going to meet at this point over here, because all the perpendicular lines, that is perpendicular bisector, is nothing but a perpendicular line that is drawn from the center of this side of a triangle, and all these perpendicular bisectors are going to meet at this point. So this point is noted. Similarly, you can see in this triangle also perpendicular bisectors are going to meet at this point. So perpendicular bisectors for all of these triangles formed by these rain gauges are going to be marked, and then finally a polygon is going to be generated. This polygon is connecting all these the meeting point of all these perpendicular bisectors, and this one area is going to give the rainfall that is collected in this rain gauge station 1 is going to be representative of this area of the drainage basin. Now, if you see, the second area doesn't have an outer boundary that is formed by any triangle. So the boundary of the drainage basin itself will form the one side of the polygon. So this line, this yellow line, this blue line, and this line all together is going to form the polygon, the area that is representative by this rain gauge number 2. Similarly, rain gauge 4 is going to have this area under consideration. Rain gauge 1, 2, and 4. So this is how Thiessen's polygon method works. And and then after finding out the areas, weightages is given. That is, we know that for this one rain gauge station, this is the area. So that will be A1, and the precipitation that is obtained from this rain gauge is going to be P1. So A1 into P1, plus similarly for this rain gauge station, this is going to be the area. So this rainfall into this area will be considered, and the average of this product will be found out and divided by the total area of the drainage basin. So here what we have to keep in mind is this A, the A without any notation of the numbers is going to be the area of the drainage basin, and it is not going to include any area of the polygons that are coming out of the boundaries of the drainage basin. It is only representative of the area of the drainage basin. So using this formula, we can find out the mean rainfall over a drainage basin, and this method is called the Thiessen's mean method. Now the third method is called the isoheital method. Isoheital method is nothing but a method that involves creating isoheights. Now isoheight is nothing but a line, it's a contour line. It's like a contour line. Instead, isoheight is a line that will connect all points of equal rainfall. Now, if a rain gauge is giving us 10 centimeters or 10 mm of rainfall, another rain gauge is giving us 10 mm of rainfall, and there is another one in the adjacent area giving 10, all a line that is connecting all of these points having equal rainfall is called as an isoheight. Now, in the isoheight method, what happens is this you see this is the drainage area. In this drainage area, isoheights are made based on the amount of rainfall. That is, a line connects the equal amounts of rainfall. Isoheights are formed, and here also you find an isoheight. This area that is formed between two isoheights and the boundary of the drainage area will be A1, and then this rainfall will be P1. This is going to be P2. Similarly, this area is going to be A2. This will be P2, and this will be P3. That is, P3 rainfall is equal to 12. P2 is equal to 11. P1 is equal to 10. So using this formula, that is, area will be A1. A1 will be P1 plus P2 by 2. That is 10 plus 11 by 2 into this area. 11 plus 12 by 2 into this area. 12 plus 13 by 2 into this area. All of these quantities are going to be added, and the average is going to be found out. And then it is going to be divided by the sum of all of the areas of the isoheight, or the total drainage area. And this is one way, another way of calculating the mean rainfall for a drainage basin. Now, this is one of the most elaborate, and it is also most accurate method of estimating the mean rainfall for a drainage basin. So we talked about three methods: arithmetical mean method, Thiessen's mean polygon method, and isoheighting method. The answer for this question would be which is the most accurate method of rain gauging. It will be isoheightal method, and sorry, the option C is the answer. This is an error that has come from my part. So isoheightal method will be the most accurate of rain gauging method. So option C is the correct answer. Okay. Moving on to the next question. Which of the following is a non-recording gauge is the question. You can put in your answers in the chat box, and then we'll discuss it. Okay, so I've got A and D as the answer. We can see what uh, what is the solution for this question. So before that, let's take a look into what are the what is this rain gauge? I mean, what are we just talked about? What are rain gauges? They are measuring devices to measure rainfall. There are two categories of rain gauges. One is the non-recording gauge, and another is the recording gauges. Non-recording gauges, as the name suggests, it is a measuring device that can only collect the rain, and the measurement has to be done manually. So what you see here is the one of the recording gauges, non-recording gauges that is widely used in India that we have within our syllabus to learn about. It's called the Siemens gauge. Siemens gauge is basically like a cylinder with the funnel and a collecting bottle inside. 12.7 centimeters is the diameter of this cylinder, and around 30.5 centimeters depth is there. Within that, you see there will be a funnel. This funnel is going to collect the water, and this water is going to trickle down into or flow down into this collecting bottle. Once the depth of the water, or once the bottle is filled, that no, I don't think it is being filled after a certain depth. The collecting bottle, water from the collecting bottle is transferred into a measuring jar, a cylindrical, graduated cylindrical jar, and the rainfall is measured manually. So this is called a non-recording gauge, and its name is called Siemens gauge, which is used in India. Now, this has an accuracy of 0.11 mm. Rainfall is measured every day. The rainfall measurement time is starting from 8:30 a.m. to the next day. So 24 hours of rainfall means the rainfall that is measured from 8:30 a.m. in the morning till 8:30 a.m. in the next day. When the collecting bottle cannot hold more than 10 centimeter of rain, so frequent readings have to be taken when there's excessive, very heavy rainfall. Otherwise, until the 10 centimeter of rain is reached, we can keep the bottle and then keep collecting rainfall after 10 centimeter of rain is achieved. Now, recording gauges, again, like the name suggests, are gauges that not only collects, but it is also it is also having a mechanism that can automatically record what is the intensity of rainfall or the depth of the rainfall that is occurring. There are mainly three types of rain gauges that is used in India. One is a tip in bucket type, second one the weighing bucket type, and third one is the float recording type, or it is also called as the natural siphon type. We'll go into detail in the coming slides with a couple of more questions. So these recording gauges are making a continuous plot of this rainfall occurring. That is, we are not going to collect the bottle. When the rainfall occurs, there are mechanisms for all these three types of recording gauges to take the measurement as and when the rain is occurring. So continuous monitoring or continuous plot of rainfall is occurring. So it is not giving us intermittent rainfall quantities, but continuous plot. So it is going to be the cumulative rainfall. So first there will be 1 centimeter, then 2 centimeter, 3 centimeters. So totally we are going to get a reading of 3 centimeters and not the discrete values. So the non-recording gauge out of these four options is the Siemens gauge, tipping bucket, weighing bucket, and natural siphon type, or float recording type are three types of recording gauges that is used in our country. Next question, is this statement true or false? Vegetation affects rainfall. Is the statement true or false? Okay. The statement is true. Vegetation does affect rainfall. It is going to form as an obstruction to the water that is flowing. Not only that, vegetation can also help in water. I mean, it is going to reduce the rate with which water is going to flow So this can also help in the infiltration process, help support the infiltration process. So vegetation does affect the runoff. Now, which type of rain gauges are used by the US Weather Bureau? Are they Simon's gauges, tipping bucket type, weighing bucket type, or the natural siphon type? Okay, so moving on. So we talked about the non-recording gauge called the Simon's gauge in detail about what is the dimension of the opening, what to what depth it is, what is the general depth of the Simon gauge and how it works, at what level is the water transferred, and what happens when there is a very frequent rainfall. Now, going into a bit of going in detail into these recording gauges, the first type we are talking about is a tipping bucket type rain gauge. Now, tipping bucket type, again, as its name suggests, there is a bucket that tips whenever the water reaches 0.25 mm of rain. When the bucket has achieved a 0.25 mm depth of water or received 0.25 mm depth of water, it will tip and it will transfer the water to this measuring jar. And then again, it will go back to its original position until water keeps falling into it. And again, when 0.25 mm reaches, it will tip. So this is why it is called a tipping bucket type. So how is this recording? How is this a recording gauge? There is a mechanism, a pen and paper mechanism that is attached to this tipping bucket. So every time the bucket tips, there is a hike or a change in the graph that is being plotted, and this is how the measurement is done using a tipping bucket. So once this measuring jar is filled, they will remove the water and then keep it again for collecting this water. So these are the dimensions. It is a 30 centimeter diameter gauge, and this is the tipping bucket type is used by US Weather Bureau. It is also used in our country. Now, so the answer for this question is the tipping bucket type, which is option B. We'll also look into what is the weighing bucket type and natural siphon type in the coming slides. So rainfall is also known as what? Is it called downpour, precipitation, condensation, or infiltration? Pretty simple question. Okay, so the correct answer is precipitation. Very obvious question. Precipitation includes rainfall, drizzle, light rain, heavy rain, snowfall, and everything. So rainfall generally, when we talk about precipitation, uh, it means rainfall. Uh, so rainfall can also be called as precipitation. Sixth question. A float chamber type catch is used in which of the following type of rain gauges? Is it in the tipping bucket type, weighing bucket type, natural siphon type, or non-recording gauge type? So we learned about what a non-recording gauge type is. We also learned about a tipping bucket type. So based on this, you can just think about whether float type chamber is available in any of the two, and then choose the appropriate option. Okay. So we talked about tipping bucket, we talked about non-recording gauges. Let's talk about the other two remaining, the weighing bucket type or natural siphon type of float chamber, float recording type of rain gauge. Now, weighing bucket type is again a bucket, again rain gauge that is through the help of a funnel. It collects water in a bucket which has a weight attached to it. So, as more and more water enters into this bucket, the weight is measured. It keeps going down, and there is a pen and paper mechanism that is attached to this weight system in here. And as the weight increases, this as the weight increases, the pen goes up and up, and then again when it decreases, it goes down and down because of this that is how the mechanism works. And again, this is also giving an accumulated plot of rainfall versus time. So this is why it is called a weighing bucket type. Then the natural siphon type is also it is also called the float type gauge. So the answer for this question, correct answer for this question will be float type gauge. In this natural siphon type, again a funnel is going to collect water from it is going to enter here and it is going to get transferred to this float chamber. In this float chamber, there is a float attached, and this pen and paper setup is attached to this float. So as the amount of water increases, the float will keep coming up. And then after a point of time, this siphon type will empty the water. The siphon system is going to empty whatever water and the float is going to come down again. So this is called the float type chamber or the natural siphon type. And here the pen and paper setup or system is attached to this float, and it is also recording. It's a continuous work, so it is recording and the accumulation of rainfall against time. So the correct answer for this question would be option C, natural siphon type. It is also called a float type recording rain gauge. So, and uh, the name float itself should bring this type of recording gauge into your mind. So it's a natural siphon type or float type rain gauge. Next question. How is the intensity of rainfall measured? Is it done using continuously recording gauge, an anemometer, hydrometer, or a seismometer? Okay. So, like how we have discussed, intensity of rainfall is measured using rain gauges, two types, recording, non-recording. Recording rain gauges are all continuously recording the rainfall, so it can also be called as continuously recording gauge. Apart from that, anemometer measures speed of wind and pressure of wind. Hydrometer is used for measuring the characteristics of liquid. Seismometer is used for measuring the movement of the earth or the motion of the ground during a earthquake. So the correct answer for this question will be option A. Now, what do you call it when the annual rainfall is greater than the average annual rainfall? Is it called a good year, a bad year, a very good year, or a very bad year? For those of you who joined late, you can put in your answers in the chat box, and then we'll be discussing about the solution. Okay. So uh, there are two. There are different terms here which might not be very familiar to us, which is basically annual rainfall average annual rainfall. What is the difference between these two, and what are these good year, bad year, very good year, and very bad year? Are they just simple terms used, or do they have any significance or meaning when we use it in uh, hydrology? So, when we use rain gauges and measure the amount of rain that is collected in one day or 24 hours, that quantity is called the daily rainfall. Now, if you are considering 1 year, you will have 365 values of daily rainfall. The total amount of rainfall that is collected in 1 year is called the annual rainfall. Now, we also have a term called the average annual rainfall. Average annual rainfall, as the term suggests, is probably the average of all these annual rainfalls that are obtained. But when we say average, over what period of time is what is important over here, and it is for a period of 35 years. Now, when we consider it is one rainfall cycle period is considered to be 35 years. So the annual rainfall for 35 years is obtained, and it is divided by 35, and that quantity so obtained is called the average annual rainfall. Another name for this average annual rainfall is called normal annual rainfall or normal rainfall. So if you see the term normal rainfall or average annual rainfall, it means that annual rainfalls of 35 years are averaged for a period of 35 years, and that value is representative of the rainfall for that particular area. So when we say that this area gets 10 mm of rainfall, it means that for 35 years, that is the average of all the annual rainfall that is obtained for 35 years has been 10 mm. So again, another term used for this is normal annual rainfall. Now, what is the significance of this quantity? Now, say suppose 1 year we are getting 10 mm and the second year we're getting 20 mm. The average annual rainfall is 10 mm. But so based on this quantity of average annual rainfall, comparing it to the annual in relative to the average annual rainfall, we can know if that year whether we have obtained a good amount of rainfall or a bad amount of rainfall. So that is the threshold or a set value to compare what is the state of rainfall in a particular year. Now, for that, the index that is used is called the index of wetness, which is the ratio of the actual rainfall in a particular year in a particular place to the normal rainfall. So this average annual rainfall coming in the denominator, and the annual rainfall for that place in that particular year will come on the numerator, and the ratio between these two values is called the index of wetness. Now, index of wetness, again, ratio of actual rainfall in a given year at a given place to the normal annual rainfall at that place. Now, again, like I said, it is giving us how much of water deficiency we've had in that year or how much in excess we have had in that year. So if we get a 60% of index, it means we are deficient of 40% of rainfall. So if the deficiency is around 30 to 45, we say that it's a largely deficient year. And again, if it is going to 45 to 60% deficient, I'm not talking about the index of wetness. When you get the index of wetness as 60%, it means 40% deficiency. So if this 40% is around 45 to 60%, we see that it is a serious deficiency, and more than 60% is a disastrous state that is associated with droughts and everything. So if the annual rainfall, that is the annual rainfall, is less than the average annual rainfall, we say that it is a bad year. Now, if the annual rainfall is almost equal to the average annual rainfall, we say it's a normal year or an average year. But if the annual rainfall exceeds the average annual rainfall, we say it's a good year. So if the average annual rainfall is say 10 mm, you get 12. A particular year you get 12, then we say it's a good year. For a particular year, if you get 9, we say it's a bad year. If it is equal to 12 itself, 10, we say that it is an average year. So this is an important concept in this lecture series, index of wetness, what is deficiency, and what is it called when the annual rainfall exceeds or goes below the average annual rainfall. So the answer for this is when annual rainfall is greater than average annual rainfall, we say it's a very good year or a good year. Sorry, very good and very bad and all is not there. Good and bad and average is there. C and D options are invalid. There is nothing called very good or very bad year. Okay. Ninth question. As per the IS recommendation, the rain gauge density for a plain region is given by which out of the four options? Do we need to keep one station for every 520 kilometers square, or is it one station for every 620 kilometers square, one station per 260 kilometers square, or one station per 130 kilometers square? I'm putting your answers in the chat box. Okay. So in order to know how many rain gauges we need to provide in a particular area, there are a lot of factors that you need to take into consideration. One is the topography, whether it is a slopy area, steep area, or a plain area. And there are so many other requirements of considering how many rain gauge stations or rain gauges need to be placed in a particular area. So now the if you say we are using only 3 rain gauge stations in a plain area, the rain is going to be higher in towards the mountain region. So in placing 3 rain gauge stations will not give us accurate estimates of the uh, rainfall for a mountainous region when when you compare it to a plain region. So for those regions, we'll have to place more rain gauge stations. So based on that, there are the Indian standard codes are giving us some recommendation, and they say that plain region needs one station for every 520 kilometers square. A region having an average elevation of 1000 meter needs one station per 260 to 390 kilometers square, and hilly and areas with heavy rainfall need one station every 130 kilometers square. So this is the recommendation, IS recommendations for rain. We say this rain gauge density, the number of rain gauges per area, rain gauge density, and this is the recommendation for that. Plain region for every 520 kilometers square, average elevation of 1000 mm, 260 to 390 kilometers square, we need one station. Hilly and heavy rainfall areas, we need a station per 130 kilometers square. So if we are calculating the rain gauge stations, you have to multiply the area into the rain gauge density. Then we'll get the number of rain gauge stations that are required for that particular area. So if there's a question coming saying that we have been given a plain area with plain region with area of 520 kilometers square. How many rain gauge stations are required in such an area? Then you will multiply, you will divide the total area given by this value 520, 260 or 130 based on the area that is provided, and then find the number of rain gauge stations. You can take a note of this point on the slide. So here, as per IS recommendation, the rain gauge density for a plain region is given as one station per 520 kilometers square. This value is for regions with average elevation of 1000 meter, and this one station per 130 kilometers square is for regions hilly and heavy rainfall region. Now this is a very simple numerical. Please do this and post in your answers in the chat box. There are 4 rain gauge stations in a drainage basin, and the average annual values at these stations are 800, 620, 400 and 540 mm of rainfall. What will be the mean rainfall? We discussed about various methods of calculating mean rainfall. So in order to understand what method you need to use, you have to see what is the data available. If you have the data of area and weightage and all, you can use the Thiessen's mean method or isoheitel method and stuff. But if you don't have any area information given, you can just do the arithmetic mean method to find out the mean rainfall. Please do this and post in your answers. This will be helpful for you. I mean, you won't have to. The numericals in this problem solving sessions will actually are consistently coming in question papers every year. So if you understand and practice it now, you won't have to do a practice a second time or later on when during the exams. So try your maximum to do the numericals during the problem solving sessions. Okay, this is a very simple problem. So yes, your answer is right, Muttaram. It is 590 mm. You just add the four numbers and divide it by 4 and you will get 590 mm. This is a very simple numerical that can come. Next question. In which of the following rain gauging method is contour joining the points of equal rainfall done? Is it in the arithmetic mean method, Thiessen method, isoheitel method, or recording type? Correct answer. So we talked about three methods: arithmetic mean method, which is nothing but finding the average, adding all the precipitation value and dividing it by the number of values that you have. Thiessen's method, as I explained, is you're creating polygons using perpendicular bisectors of triangles that are formed by connecting the rain gauges. Isoheitel method, we are forming closed areas by isoheights that connects uh, all points of equal rainfall. So this contour joining points of equal rainfall is used in isoheightel method. So option C is the correct answer. Some more facts associated with isoheights. Two isoheights never cross each other because again, it will never be crossing each other because it is connecting lines of equal rainfall. So it is not going to cross with another value. Then each isoheight closes on itself. That is, it is never going to be open. It will form a closed loop like a contour itself. And isoheights of higher value indicates higher rainfall, obviously. So the answer for this option is C. Next question, what is a hydrograph? What does it give us? Is it cumulative rainfall versus time, rainfall depth versus time or duration, rainfall intensity versus time, or is it discharge versus time? Correct answer, Punkte. It is rainfall intensity versus time. So hydrograph is a graph, a bar chart that is a plot basically between the intensity of rainfall versus the duration. It will look like this. And last session we had learned about what hydrograph is. It is discharge versus time. So rainfall intensity versus time is hydrograph. Discharge versus time is hydrograph. Now, the rainwater in a gauge shall be measured every day at what time? At 8:30, 10:30, 7:30 in the night, or 8:30 in the night? 10:30 in the night or 8:30 at night? Okay, correct answer is 8:30. So we had seen in the initial slides about the non-recurring gauges. The measurement time starts at 8:30, and if when we consider 124 hours, the 24 hours is the time between 8:30 in the morning to 8:30 next morning. So 8:30 a.m. is the correct answer. Okay. Now this is again a numerical. A catchment is having 5 rain gauge stations. What is the number of additional stations required if a 6% error in estimation is allowed and a coefficient of variation of 20 exists? I'll just give, maybe you can do this numerical after I give the equation. So in order to know, like we had decided based on the type of area, the IS has recommended that this many number of, there should be one station for every 520 kilometers square. But there is also a requirement to determine what is the best number of rain gauges that is required for places. If you place a huge number of rain gauges, maybe the measurement accuracy uh, is going to be compromised. Similarly, even if we place only very less number of rain gauges, again, that is also going to affect the estimation of rainfall values. So in order to optimize the number of rain gauges that is required to be installed in an area, we have this formula called N is equal to CV by E the whole square. Here N is the optimum number of rain gauge stations, rain gauges that is required. CV is the coefficient of variation of rainfall. I'll show you the formula of obtaining coefficient of variation. For this question, it is already given. So you just need to use this equation. But this term means it's a coefficient of variation of rainfall based on whatever existing rain gauge stations data that we have. E is the percentage of error that is allowed when estimating the mean rainfall. So if we have these two quantities, we can know what is the optimum number of rain gauges that is required for a particular area. So CV by E, CV is the coefficient of variation, E is the percentage error that is allowed, N is the optimum rain gauges. So please do this problem and put in your answers. 5 rain gauges is there, 6% error is allowed, 20 is the existing, 20 is the coefficient of variation from data from this 5 rain gauges. So how many additional stations required is what is asked. We already have 5, but they want to know how many additional is required. Okay. So yeah, you're right. Answer is right, Muthuram. It is 7. So let's see the calculation. So like I said, we have already 5 rain gauge stations. Out from that, we are getting that the coefficient of variation of rainfall that is calculated from this 5 rain gauge station is 20. Error allowed is 6%. So optimum can be found out by dividing 20 by 6. CV by E the whole square, which will give us 11.11. So that is not a whole number. So we take it to the next highest number, which is 12. Now already 5 gauges are there. So what we do is we subtract 5 from 12 to get 7. So additionally, along with this 5 rain gauge stations, we have to place 7 more rain gauge stations so that we get optimal measurements for rainfall. So this is how this problem is done. There's one more problem. You can do this also and post in your answers in the chat box. Again, here they're saying 6 rain gauge stations in catchment was having a coefficient variation of 29.54. What will be the optimum number of stations required for a 10% error in the estimation of the mean rainfall? So I've got two answers, 9 and 3. So let's just check what is the correct answer. Now, I had told initially, I'll give you the formula for CV. So CV is the coefficient of variation, and CV is obtained as by dividing the mean of the rainfall by its standard deviation. Standard deviation, if you're familiar with probability between statistics, we find it by subtracting the value. That is, suppose we have a particular value, then we subtract that value from the mean of all. We have 10 values. If one value is 5, another value is 10, if another value is 20, then and the mean is say 15, we minus 5 minus 15 the whole square divided by n minus 1, and the sum of all of that to the root will give us the standard deviation. Now the standard deviation divided by the mean precipitation into 100 is giving us the coefficient of variation. Now here in our calculation, coefficient of variation is 29.54. Error is 10%. So direct substitution into this 29.54 divided by 10 will be 2.954 the whole square. And you get 8.72. Again, converting into a whole number, you get 9. Now, what happened here with Punguday is that, just a second, that since you gave the answer 3, I think it is because all they have given that 6 rain gauge stations are there. But here in the question, they have asked what is the optimum number of stations that is required. That is 9. What is the additional number of stations that need to be placed will be 3, because there is already 6 rain gauge station. Additionally, we'll need to place 3, but be careful of the what question they're asking. It's optimum number of stations is what they have asked, whereas in here they're asking you what is the additional number of stations required. In that case, you have to minus whatever is the existing number of rain gauge stations from the optimum. Whereas here they have not asked us to find how much additionally stations are required. So based on that, it is just a matter of a simple step. The option that you select will be wrong. So be careful when it comes to what they're asking in the question. So thank you for that. And next, what is a mass curve of rainfall? What kind of plot is obtained for a mass curve of rainfall? Is it accumulated precipitation and time in chronological order, or accumulated rainfall intensity versus time? Is it rainfall intensity and time in chronological order, or none of these? The first one is accumulated precipitation versus time. Another one is accumulated intensity versus time. Another one is rainfall intensity versus time in chronological order, or is it none of these? Okay. So what is this mass curve of rainfall? It is nothing but that data that we get from recording gauges. We said that the recording gauges are continuously recording data, and the data obtained from these recording gauges is basically the mass curve of giving us information about the mass curve of rainfall. So it records the flow time and weighing bucket type are of this form. So here what is happening is, in the chronological order, what is the accumulated precipitation? As in the first day this much precipitation, then second day this much precipitation. In decreasing order of time, the plot is plotted, and it is between the accumulated precipitation, not intensity. You can notice the unit over here. It is centimeters. It's a depth and not the intensity. Intensity means it is centimeter per hour. We can obtain the intensity of rainfall from this accumulated from this mass curve, but the plot is between accumulated precipitation versus time in chronological order. So correct answer for this would be option A, accumulated precipitation and time in chronological order. It is not a plot of intensity of rainfall. So we'll take a 2 to 3 minutes break. It is 7:02 now. We'll be back here at 7:05. Yes, correct answer. If the intensity of rainfall is more than the infiltration capacity of the soil, then the infiltration rate will be no. I mean, it's not the correct answer. Let's check the answer. So, what is infiltration? Infiltration is basically the flow of the water into the ground from the ground surface. Infiltration capacity is what is the maximum rate with which the soil water can flow inside the soil. Now, say suppose its infiltration capacity is 10 centimeter per hour. Now, rain is falling at the rate of 20 centimeter per hour, then all of that water is not going to go into the soil because the infiltration capacity of the soil is only 10 centimeter per hour. So in 1 hour, only 10 centimeter of this 20 centimeters of water, may say only 10 centimeter will go inside the soil. So that maximum rate at which the soil can take up water in a particular time is called the infiltration capacity. Now, what is important to be noted with respect to the infiltration capacity is if the intensity of rainfall, like I said, if the uh, intensity of rainfall is greater than the infiltration capacity, then the rate of infiltration will be equal to the infiltration capacity. It is not going to be equal to the rainfall intensities, the rate at which rainfall is occurring. So, what is the maximum rate of infiltration? If it is say 10, then even if there's a rainfall intensity of 20 occurring, only 10 centimeter per hour of 10 centimeters of rainfall will be absorbed into the soil in an hour. So infiltration rate will be equal to the infiltration capacity if the rainfall intensity is greater than the infiltration capacity. Now, if the if the intensity of rainfall is less than the infiltration capacity, then the infiltration rate, the rate with which infiltration is occurring, will be equal to the rainfall intensity. Because say if 10 centimeter per hour is the infiltration capacity of that soil, and if rainfall is occurring only at 5 centimeter per hour, then all of the water will go. So 5 centimeters of water will go into the soil because it has got a higher capacity. So in that case, the infiltration rate will be equal to the rainfall intensity and will be less than the infiltration capacity. So these two are some things that you have to understand, link, and learn. So in this question, the correct answer will be if the intensity of rainfall is more than the infiltration capacity, then the infiltration rate will be equal to the infiltration capacity, not more than the infiltration capacity. Now, next question. What is the Horton's infiltration capacity equation? Which option out of this gives us the Horton's infiltration capacity? Okay, let's move on to the answer. So infiltration capacity rate curve is basically giving us, it's a decaying curve. A decaying curve is nothing but a reducing curve. And some expressions that give us an idea about the shape of that infiltration curve are Horton's equation, Phillips equation, Kostikov's equation, and Halton's equation. So be careful with this A and D. There is an equation called Horton's equation, and there is also an equation called Halton's equation. Let's see what Horton's equation is. Here we are talking about Horton's equation. What is the correct expression for Horton's equation? It is the infiltration rate. Okay, here it is given the infiltration capacity in inches per hour is at a particular time is given by the the minimum infiltration capacity FC plus F naught minus FC. Here F naught is the initial infiltration capacity into e to the power minus k into t. K is a constant that is depending on the type of soil and the vegetation cover available in that area, and t is the time from when the rainfall will start. So if you see this curve, if you need to find out the infiltration capacity at a particular time t, then if we know the initial infiltration rate, minimum infiltration capacity, and the initial infiltration capacity, we can find out what is the F of T. So this expression is given by Horton. So the correct answer for this question would be Fc plus F naught minus Fc e to the power minus kT, which is option 4. Okay. Now, which type of rain gauge is providing a continuous plot of rainfall against time? Is it non-recording gauge, tipping bucket, weighing bucket, or recording gauge? Okay. So the correct answer is answer D. So you might wonder tipping bucket, weighing bucket, and what is the difference? Both of these are recording gauges. So all types of recording gauges give us continuous plot of rainfall against time. The only thing that is not giving us a non-recording tape. So that is why it's option D, because all of the recording gauges gives a continuous time, not just tipping bucket or weighing bucket. Again, this is a question on the equation. Which equation is used to calculate infiltration capacity using soil moisture and vegetation cover? Okay. So we just now talked about the Horton's equation. If you see here, there's a constant K which is based on soil type and vegetation cover. So the correct answer for this question would be Horton's equation, option D itself. Now, what does the W index represent in terms of infiltration? Is it the average rate of infiltration during heavy rainfall? Is it the average rate of infiltration during a light rainfall? Is it just the rate of infiltration in catchment area or infiltration rate from an infiltrometer? Okay, so let's talk about what these infiltration indices are. So, in order to compute what is the infiltration infiltration rate from the rainfall, the hydrograph or rainfall data, we have indices called the infiltration indices. So this is giving us an average infiltration rate. There are two indices. One is the phi index, one is W index. So you see here the amount of rainfall in excess of this line. This horizontal line here is what is giving what is called as a phi index. So any rainfall that is coming above this phi index is called rainfall excess. That is, this rain is going to go off as runoff, and all the values that are coming under this phi index value will go as infiltration. So this is what is the significance of this phi index. phi index is giving us the average rate of infiltration, which above which any rainfall will go off as rainfall excess, and below which all of that water is gone off as infiltration. So here all the unshaded area, that is this bottom area, it is representing all the losses, including not only infiltration, interception losses. That is when water falls, the leaves, the canopy is going to intercept this rainfall, and some of the water is going to lie on the surface. It is going to trickle down to the stem, but it is not going to reach the ground surface. Then there are depression storages. Water won't run off. There will be small holes where water will stay, and also infiltration. So all of these are included. All of the water losses because of this is included, and any water coming in excess of this line is going to go off as runoff. Now there's one more index called the W index. W index in what happens is giving us the rate of infiltration when rainfall exceeds the infiltration rate, and here the total losses due to interception and depression storage is also taken into consideration. So here, if you are calculating, you're calculating all of the losses together, but here the losses are removed. That is, interception and depression losses are also removed, and only the average infiltration rate or the infiltration loss is obtained using a W index. So W index is more accurate than the phi index because interception and depression losses are not part of infiltration. So that value is also removed, and we are obtaining only exclusively infiltration values. So the correct answer for this is option 8 is giving us the average rate of infiltration during heavy rainfall. Now, why not light rainfall? We talked about how the infiltration rate, when it is less than the intensity of rainfall, when the rainfall intensity is less than the infiltration capacity, all of the water is going to go as infiltration. But in during heavy rainfalls, we want to know what is the average infiltration rate, and after that rate, water is going to go off as runoff. So what is that average rate of infiltration? This is a question making use of this formula of phi index. Now, if you see here, phi index formula is P minus R by T. This S value won't be there, but P minus R by T. You can see the unit P is in centimeter, R is in centimeter, and W index you will get in centimeter per hour. So making use of that formula, please calculate what is the phi index. That is 30-minute period. Every half an hour, there is a rainfall occurring of intensity 5, 6.5, 8.5, 7.8, 6.4, 5.1, 5.5, and 6. So the total duration of all these rainfall would be 30 into 1, 2, 3, 4, 5, 6, 7, 8, which is 4 hours. Now, considering the phi index is also given, you need to find out what is the rainfall and what is the runoff here. Please do this problem. This will be very helpful for you to understand how these phi index and W index problems are done. So go ahead, do and post in your answers here. Okay, maybe I'll just show how this one is done, so that next problem you can do on your own. So you see here, the phi index is given by P minus R by T. So how do we calculate the rainfall, total rainfall that is occurring? We need it in centimeters. So just add all the values and multiply it with the time. So if this quantity, if we need to get it in centimeter, we will multiply 5 into 0.5. That is 0.5 hours or 30 minutes. Plus 6.5 into 0.5 plus 8.5 into 0.5. When you do all of that, the total rainfall that you get is 25.4 centimeters. Now they're asking us to compute the runoff. The phi index formula is P minus R by T. P is in centimeter, R is in centimeter, T is in R. So we have the phi index 4.5 centimeter per hour, 25.4 centimeters minus R divided by 4 hours. Although this is given, I was just showing how this value, we are obtaining this value. That is 8 rainfall events are occurring in at half an hour interval time. So totally in 4 hours is what this entire rainfall is available. So by rearranging the terms, you can find out that R is equal to 7.4 centimeters. And so the correct answer would be option B, that is 25.4 centimeters and 7.4. So this is an important formula for phi index, P minus R by T. Again, when it comes to W index, we'll have one more term, which is P minus R minus S by T, where S is the interception and depression storage. Now, what does the precipitation refer to? All forms of water that reach the earth from the atmosphere, movement of water within the soil, upward movement of water from soil, or process of water vaporization. Simple question. Correct? So, all forms of water that reach the earth from the atmosphere is called precipitation. Snow, drizzle, light rain, heavy rain, anything is precipitation. So both of you have given the correct answer, Mungutai and Mutturaman. Now, what is the primary purpose of a hydrograph in hydrology? It represents the intensity of rainfall against time, or it is estimating the number of rain gauges in a region, measuring the coefficient of variation of rainfall, or determining the average annual rainfall in a catchment. So, correct answer is A. Pungutai, correct answer. It is representing the intensity of rainfall against time. Now, what does the mass curve of rainfall represent? Accumulated precipitation against time, average annual rainfall in different regions, intensity of rainfall versus time, or infiltration capacity of different types of soil. Correct answer, it is accumulated precipitation against time. We had talked about what a mass curve is. Accumulated precipitation versus time, and accumulated precipitation is plotted in chronological order. So correct answer is option A. Now, what is the phi index used to determine? Average rate of infiltration during runoff, total losses due to interception and depression, rainfall excess in a catchment area, or the minimum network density of rain gauges. We talked about phi index is basically giving us an idea about the average rate of infiltration in an area, and anything excess of average rate is will be rainfall excess. So it is used to determine the rainfall excess in a catchment area. Phi index is basically giving us an idea about what is the average rate of infiltration. But we using that, what we can find is how much of rainfall excess is occurring in an area. Now, which type of rain gauge does not produce a continuous plot of rainfall against time? Is it Simon's gauge, tipping bucket, weighing bucket, or natural siphon type? which is not producing a continuous plot of rainfall against time. Okay, so Simon's gauge is a non-recording type. Tipping bucket, weighing bucket, and natural siphon type are all recording type. All of these three gives us continuous plot. The question is which does not produce, and the answer is Simon's gauge. Option A is the correct answer. Now here is a problem again to find out the phi index. Like how we had done earlier, please do this problem. You know the formula of phi index, it is P minus R by T. Please find out the answer and post in your answers in the chat box. So here you see the storm interval is 1 hour. First hour, in the second hour, third hour. So totally for how many hours? 8 hours a storm is occurring. And rainfall intensity is given. So whenever we use it in the formula, it is important that you use the depth, not the intensity. So you should convert this intensity value to depth and then use it in the formula to find out the phi index. Yes, let's check this problem. So first we are finding out what is the rainfall intensity, that is P minus R by T. You have to multiply and find the depth. Um, no, this is not right. Okay, 20, it is 0.8 into 1 point plus 1.8 into, yeah, I mean, basically you're multiplying it. So add all of these and 20 minus that divided by, give me this. 1 second, this calculation is not right. 8. Yeah. So this is how it goes. So we are doing 20 minus the total of this rainfall is 11.6 divided by the time duration is 8 hours and you get 1.05 centimeter per hour. Now you see that 1.05 centimeter per hour in this rainfall intensity plot comes at this point, and we see that there is one rainfall which is way far below than 1.05, and also this rainfall that is 1 centimeter per hour which is less than uh, the average infiltration rate. So this is not going to contribute to the runoff in any way. So what we have to do is in order to find out the proper average infiltration rate, we have to remove these two values. That is this value 0.8, which is less than 1.1 centimeter per hour, and 1, which is less than 1.1 centimeter per hour. And also remove that duration from the calculation. So it is actually using us to helping us to determine the rainfall excess. Since these two values that are occurring over here is not going to provide into the rainfall excess, what you have to do for an accurate estimation is remove all those rainfall intensity which is less than the phi index value that is calculated first, that is 1.05, and then after removing you have to do the calculation again. So from 20 you're going to first remove a 0.8 and 1. 20 minus 0.8. So from 11.6 you will minus 0.8 minus 1, which is 9.8 divided by 6. Okay, this is not the calculation. Let me help you with the calculation here itself. So first we did 20 minus 11.6. Here what we'll do is 20 minus 11.6 minus 0.8 minus 1. Why? Because from this value we are going to remove these two values also. Okay, so this is how we will remove these two values from this rainfall, and then also the duration. Initially it was 8 hours, but the duration also we have to remove, and in that case we will get a value of 1.7. Now if you see 1.7 is, I'm sorry, this is not 1.1, it is 1.7. So 1.7, is there any rainfall value that is less than 1.7? No. So that will be the final answer of the phi index. So in case of phi index, you should never stop the calculation by the first value that you get. You should also continue the calculation such that you remove the rainfall intensity that is coming less than this calculated value, and then once again calculate phi index by removing these two values and the duration to get one more answer. That answer is going to be the, again, that also you have to check if it is if there's any rainfall value that is less than this infiltration rate, and if it is there, again you have to remove that value also and again do the calculation. So this is a continuous process until you get the infiltration rate where the rainfall, all of the rainfall values are exceeding that infiltration rate. Until then you have to continue the calculation. So here the answer would be 1.7 centimeter per hour. This will be wrong, it will be 1.7 centimeter per hour. So this is how the phi index has to be found out. Now moving on, let's go to a question which is calculating the W index. So here a 140-minute storm is given, 20 minutes interval, 3, 3, 9, 6.16, 1.2, 1.2 and 6 millimeter per hour. Assuming that the phi index is 3 mm per hour and there's an initial loss of 0.8 mm, you have to find the W index, the rainfall and the runoff. So here they've given phi index, you need to find the W index. Extra quantity they have given is the initial loss of 0.8 mm. So you know the formula, it's it is not, we are actually, yes, I understand. 11.6 is the total rainfall. You need to minus 0.8 from 11.6, 0.8 and 1 from 11.6. 20 minus answer divided by 6 will be, okay, that calculation which I've given is not correct. You have to do it 1 second and put in the correct calculation. This is not how you have to do. This is how you have to do. The bracket comes here. Here. So in this case, it will be 11.6 minus 0.8 minus 1. you will get 9.8. 11.6 minus 0.8 minus 1, 9.8. Or if you're removing the bracket, you can write it as this, plus yeah, plus. Do you get my point? Yeah, okay, thank you. So that is how this calculation comes. It is first 11.6 minus, first you have to separate it. This is not the correct way of writing. I will write it separately over here when I publish the slides. But this is how the calculation is. First you're separating out, I mean you're subtracting these values from the precipitation, and then that value you're minusing from this. I'll when I post the the PDF files, I'll make the correction and then submit. So this question again, find the W index. W index is, for that we have the initial loss. You can use that value and find out the W index. You also have to find the total rainfall and the net runoff. So P you have, R you don't have, pi index you have, and the initial loss you have. So you can find out what is the W index, and from that you can find out the runoff. Okay, let's move on to the solution. So we see that at the 20th minute we have 3, the 40th minute we have 3, 60th minute 9, 6.6, 1.2, 1.2, and 140th minute 6. So we'll first convert all of this depth of the rainfall into mm. That is 3 into 20 by 60. That is how you're getting 1 mm. Again 3 into 40 by 60, 3 into 60 by 60. Or you can do it totally also over here. You add all of this into 20 by 60. You get 10 mm is the total rainfall. Phi index is given as 3 mm per hour. Now we see that if phi index is 3 mm per hour, we see that the depth of the rainfall here Yeah, it is. You see, it's not 3 into 40 by 60. It is again 3 into 20 by 60, 9 into 20 by 60, because the interval is 2020. This is the time at which the rainfall occurred. So you have to multiply everything by 20 by 60, and this will be the depth of the rainfall that you get. We see that phi index is 3 mm per hour. Now, what are the, which all values are going below 3 mm per hour? We see that this value, first value, is equal to. So that also needs to be removed. Second value also needs to be removed. 1.2 needs to be removed. This 1.2 also needs to be removed. So we'll remove these four points, as well as the duration, that is 2020, which is 80 minutes from the total duration, and then again calculate the uh, phi index. So here, if we remove all of this, the time of excess rainfall is only for three values, 1, 2, and 3. So we'll 3 into 20, 60 minutes, which is basically 1 hour. So precipitation is 10 mm. You have to subtract 3 plus 3 plus 1.2 plus 1.2 from it, multiply it by 20 by 60, 7.2 mm. The phi index is equal to P minus R by TE. We know it is 3. So 7.2 minus R by 1, which is again 7.2 minus 3 into 1, will give the runoff as 4.2 mm. In order to calculate the W index, again P minus R minus the loss by T. P is, now for this we are going to be using the total precipitation that we got in the beginning. When we calculate W index, all this thing of removing these values and all of that is not needed. We have to use the actual first precipitation of 10 mm minus the runoff value we got and the IA value that is given in the question, divided by the total time, which is okay. Here again, the time duration has to be taken as 1 hour only. Although we are taking the precipitation value as 10, the duration duration that has to be considered is the duration for the excess rainfall that is occurring, because it's a time of excess rainfall. T is not actually just any time; it is a time of excess rainfall. So excess rainfall occurring is only for 1 hour. Remaining precipitations are not included in the excess rainfall. So precipitation value, you have to take the first value, but the TE value, you will always have to take the time of excess rainfall, and that will give 5 mm per hour as the W index. Okay. So this is a concept that you will have to familiarize from the lecture series, the phi index and W index problem. I can, in the coming classes, I'll put in some more additional problems related to phi and W index for more practice. If there is any doubt regarding anything in this session, please feel free to ask. Otherwise, this will be the end of today's problem solving sessions. You can leave the class, and if you have any doubts, please do ask. Thank you, Pungote, for attending today's class and taking part. Okay, so thank you everyone for today's session. We'll meet in the next week, same time, Tuesday, with problems associated with the ninth week's lecture. and see you next week. Have a great week. Thank you. Bye bye.